All right, then next topic is called StatefulSets. So this is a new chapter, and it is by far the most complicated chapter in the training. I'd say this chapter is still a bit of work in progress, so it doesn't describe the stateful set in its entirety, but it also, the other chapters don't describe exhaustively the individual possibilities there are with Kubernetes and pods and replica sets. So it's for you to get a feeling for what it does. Now, in my opinion, there's already plenty material about deployments and how you treat applications in Kubernetes. So we'll spend a bit time in the tutorial about stateful sets, but we have limited time today to talk about it, which is a bit of sad. So we'll have to find out whether we can do that today or whether we'll have to schedule another session. If that's required, I'll let you notify, or I'll let you know. And if you're watching the recording, well, then the recordings will be there. So the first chapter of stateful sets is describing the concepts that have to be used to get to a stateful set. And before we do that, I would like to talk a little bit about why is the concept of a stateful set necessary. So far we've been talking about pods, replica sets, and deployments. And I stated that, in my humble opinion, applications should not have state. They shouldn't write to the file system. A pod shouldn't mount a persistent volume to write files to the file system, because a persistent volume is either backed by a shared file system, for example, something similar to NFS, or it's a block device, which is basically a remotely attached hard disk residing on some storage server. In my personal opinion, an NFS, in order to make an NFS scale horizontally, because Kubernetes clusters could be very large, like there could be thousands of nodes and 10,000s of containers. Now imagine an NFS server that will serve files for thousands of containers. You either have a high-end NFS server, or at some point it'll fail. And I don't believe that this is a good choice. This is a good approach. So if you use NFS, which is rather easy to set up, and you'll have a small environment, well, this will work, no doubt about that. I've done NFS deployments decades ago, and they did work for a while. But in the projects that I've observed that scale horizontally, so it either is one project or it's just the Kubernetes cluster that scales, horizontally very fast, at some point performance and storage space and durability gets a problem. Because how do you back up, for example, a storage server that has hundreds of terabytes of files? How do you ensure that no files are corrupted, especially if hard disks fail, and hard disks do fail? If servers go down and all that, how do you provide enough resource, a performance for write and read performance? So the tech community has thought about this problem and has solved it. So instead of using NFS, the way you deploy your application assets is using an object store. No way around it. No argument around that. If you're writing an application today, and you're writing an application that uses a file system to share information between instances of your application, that's basically poor craftsmanship. Period. It's no excuse. In my opinion, there's no excuse. there are certain circumstances where this can still be tolerated, which, for example, is if you're sure that it's a small environment and that maybe you're on premise and you don't have access to an object store, and having an object store would be too much of an hassle. But with the emerge of software-defined object stores such as Minio, which are rather easy to set up, I'm not sure whether this argument is still valid. The only other option I can see for storing files in a file system or in an NFS storage is if it's provided by your infrastructure provider. You're using the NFS protocol, but what's behind that, the backend, is horizontally scalable, it's durable, and all you have to care is buy it and fire and forget after that. Or maybe the third exception is you have a legacy application. There's no more money in the project, and well, the applications write to the file system, so that will be okay as well. But if you're writing new applications, use an object store. Object stores for on-premise purposes are, for example, OpenStack, the OpenStack object store, formerly known as OpenStack Swift. They are not exactly file systems. That's why they're called object stores. They provide you with a simple REST API to store and retrieve objects. And objects means binary large objects. So it could be small objects like images, little profile photo, but they could also be large objects, such as, for example, operating system images that could be several gigabytes of size. The object store will take care of the distribution of your assets in terms of sharding and replication. So it will chunk your file into little pieces, and even if the client is written properly, it will chunk that reading and streaming to several servers simultaneously, which will give you a good write performance. It will chunk the data, scatter it across the cluster with replication, so that each piece of your information will reside the specified number of times. So a good object store allows you on a per object, or at least on a per bucket level, describe how many replicas you want. So you could have a bucket that replicates objects, or even an object that is replicated 3 times, and another object is replicated 5 times to improve durability. Once you store objects on the object store and you want to retrieve it, the object store can retrieve from various different physical nodes simultaneously, and underneath that from various different hard disks simultaneously, so that you'll get a striping and mirroring like approach, if you're familiar with those terms from physical hard disk arrays. So object stores usually horizontally scale very well. A lot of them, they scale into the scale of petabytes. So for both read and write performance, they scale very well. And also adding more nodes will give you more capacity in terms of storage space. So object stores, the primary way on storing assets of your applications. So why would you use persistent volumes? Now, deployments, replica sets, and bare pods are a poor choice when you want to run databases or other stateful workloads in Kubernetes. So I personally choose databases and other data services such as message queues, anything that stores data on disk by design, and that is not an asset that could be stored in an object store. I consider as a data service. One argument could be whether Kubernetes should be used for data services or not, because container isolation is not as solid as virtual machine isolation. But let's keep that discussion aside and assume that some people want to use Kubernetes to run databases, and let's look into the question: how would you run a database, or more generic speaking, a data service in Kubernetes? And the answer is a stateful set. So in order to run a stateful application, let's say a database such as Postgres or MySQL, you'll have to provide the database a data directory where it can store its files. Now, we have seen in Kubernetes that if a pod has failed, it can be rescheduled somewhere else and that the state of the file system will be lost. So you cannot just start up a Postgres, write to the file system, and there you go. Because if the container fails, for example, because the underlying host has been taken into maintenance, then your data will be lost. You could say then, well, let's replicate the data and create a replicating streaming cluster in Postgres, for example. But I wouldn't make that bet. You really want to have your data sitting on a durable storage device. And that's not a pod. You could then think about sharing a directory with the Kubernetes node, but the Kubernetes nodes can go away too. You have the same problem in a different color, so that's not an option. The answer to this is a persistent volume. So in Kubernetes, you have persistent volumes that is not the same as a volume. So for example, we've earlier talked about empty dirs, which is a particular way on sharing a volatile directory with a pod. So a regular volume has a life cycle that's attached to the life cycle of the pod. You delete the pod, the volume is gone. You don't care about a volume that has been mounted from a config map because the config map is persistent. You don't care about the empty dir volume mounted into a pod that's gone when the pod dies because you've inherently designed the usage of the empty dir to recognize the fact that it will go away with a pod. Now, for a database directory, you don't want that, so you need a concept that will provide you persistency independent from the lifecycle of a pod, and the way to do it is use a persistent volume. So the persistent volume in Kubernetes is, well, let's say you need to create a persistent volume as an administrator, and then an application can create a persistent volume claim to claim an existing persistent volume. So let's say you have a physical storage server with limited abilities to automatically create disks. So you could create 10 disks, block devices, export them, import them into Kubernetes, and then your applications can request access to those disks. That is what a persistent volume claim is about. So then you'd be like, what? Why should I manually create disks? This isn't 1995 anymore. And therefore there is something called a persistent volume provisioner. So that will create a on-demand creation experience for persistent volumes, so where your application creates a persistent volume claim that will then trigger the creation of an appropriate persistent volume that will then be bound to your persistent volume claim, so that you can then mount with a volume mount your persistent volume. That's complicated, but it is very well designed. Wrap your head around it. It's very useful. We'll see its usefulness throughout the session.